Imagine trying to representing the intricate details of an entire orchestra, with every musician and instrument, using only a single, flat photograph. How much vital information would you lose about the depth, the movement, and the interplay between elements? It is a bit like that when we try to make sense of data that has many, many features. The fundamental difficulty in visualizing high-dimensional data stems from a very basic constraint. Our human perception and the physical space we inhabit are inherently three-dimensional. We simply cannot directly perceive or accurately representing information that exists beyond three spatial dimensions in a visually intuitive way. Think of it this way: a point can exist on a line, in a plane, or in a three-dimensional cube. As you add more dimensions, the potential space for data points grows exponentially. This phenomenon is often called the curse of dimensionality. In high-dimensional spaces, data points become incredibly sparse, meaning they are very far apart from each other. Our intuitions, which are built on our three-dimensional experience, tend to fail us here. For instance, the concept of nearest neighbor becomes less meaningful when all points are equally far from each other in a vast, empty space. Even slight rotations or transformations in these higher dimensions can drastically change perceived relationships between data points, making it impossible to capture all meaningful aspects simultaneously on a two- or three-dimensional plot. To overcome this, machine learning practitioners relying on a suite of sophisticated techniques known as dimensionality reduction. These methods do not simply discard dimensions. Instead, they aim to find a lower dimensional representation of the data that preserves as much of the original data's structure and relationships as possible. Popular examples include principal component analysis, often referred to as PCA, which finds directions of greatest variance, and T-distributed stochastic neighbor embedding, or t-SNE, which is particularly good at preserving local relationships between data points. An intriguing concept here is the manifold hypothesis, which suggests that even when data exists in a very high-dimensional space, it often lies on or close to a lower-dimensional structure called a manifold. Imagine a crumpled piece of paper in a three-dimensional room. The paper itself is two-dimensional, but it exists within three dimensions. The challenge for visualization techniques is to unfold this paper in a way that reveals its true underlying two-dimensional form. Finding the optimal balance between preserving both local neighbors and global structures in these projections is a core research area, and techniques like uniform manifold approximation and projection, or UMAP, representing advances in this complex domain. So, while our innate human perception struggles with the sheer complexity of high-dimensional data, these advanced visualization techniques act as powerful translators. They allow us to uncover hidden patterns, identify clusters, and gain crucial insights from data that would otherwise remain as opaque. By effectively reducing complexity while maintaining meaningful relationships, we can make informed decisions and build more effective machine learning models.